All right, welcome chemists to another lecture in Ralston Valley High School Chemistry's AP Chemistry Lecture Series. Today we're going to be talking about Chapter 15, Lecture number 4, which discusses solubility. Let's get started. All right, in our recent discussions, we have been talking about applications of aqueous solutia equilibrium. This is really just a continuation of those same ideas, now applied to the dissolution of ionic solutes into an aqueous solution. So I've written for you here an expression which we are going to refer to throughout the remainder of our discussion as a dissociation equation. In this equation, we are showing a generic ionic solute, which I've labeled here as CXAY, where C stands for the cation present in the solute, and A stands for the anion. And as that solute dissolves, recall from our previous conversations, it undergoes the process of dissociation, separating apart into the component ions, that is the cation C positive and the anion A negative. Recall that that dissociation occurs because the polar water molecules in solution exert a strong ion dipole attraction to those ions. And if those polar water molecules are able to exert a strong enough attraction, they cause the ion to disassociate off the surface of the solute, and then they hydrate it surrounding that ion in solution. So as a net result, we see the cations and anions disassociating from one another into the aqueous solution. Now recall, because those cations and anions are still attracted to one another, they're going to still be able to recombine back together to reform that precipitate, which implies, therefore, the process of dissociation is a reversible chemical process. And as a reversible process, we'd expect to see this system establish a point of equilibrium. Because this equilibrium system will be established, we can describe mathematically the equilibrium system the same way we have every time, by defining a value for the equilibrium constant K. In this particular instance, we're going to call this K a value of KSP, which stands for the solubility product constant. The reason that this is defined as the solubility product is because, recall from our discussions of heterogeneous equilibrium, we only include species which can change concentration within the equilibrium expression itself, which implies we're not going to include anything which is in solid state, which is the solute on the left-hand side of our dissociation equation. And as such, the KSP for this expression would be equal to, as always, concentration of products over reactants. That would be the concentration of the cation C positive raised to the exponent power of its coefficient from the dissociation, which here is X, times the concentration of that anion A negative raised to its respective coefficient Y. Now again, my denominator will not include anything because the only species present in that denominator is the solid phase species CXAY. So as a note to yourself here, please remember we're not going to include the solids in these KSP expressions. And that's going to actually simplify things significantly, because now we only have to do with the product of those concentrations. We no longer have a quotient which we have to deal with. Now, importantly, folks, we've already qualitatively discussed solubility earlier in our year when we talked about the idea that all alkali metal compounds are soluble and all ammonium compounds are soluble. Now, that being said, even highly soluble substances have limits to their solubility. That is to say, think about the highly soluble substance table salt, NaCl. If you've ever noticed before, as you dissolve salt into water, a lot of it will dissolve, but if you add more and more and more salt to your system, you'll notice a point where the system becomes completely saturated with table salt, and any additional salt added to the system seems to just pile up on the bottom of your beaker. Now, what's really happening there is the system is reaching its point of equilibrium. In a solubility system, the point of equilibrium is the point of saturation of that solution. And once it becomes saturated, that's not to say that no more salt will dissolve, but instead that the rate at which the salt is dissolving is balanced by the rate at which those ions are recombining together to reform the precipitate. So again, that point of saturation is the point of equilibrium. And again, it's a dynamic equilibrium where dissolving and reformation of the precipitates is happening constantly at all times once that equilibrium is established. All right, so now that we have an idea about the approach we're going to use to solving these problems, there's a variety of different ways that we can see a solubility problem given to us on an AP test. I've listed for you here 5 different common types of solubility problems. Those are, first, we could ask you to calculate the solubility of a particular ionic solute, or to compare the relative solubilities of 2 different ionic solutes. Number 2, I could give you information about the solubility of a solute and ask you to calculate from that solubility data a value of the equilibrium constant Ksp for the system. Number 3, I could ask you about mixing together 2 aqueous solutions and asking to determine quantitatively if you can predict the formation of a precipitate in the system. Number 4, I could give you a mixture of ions, and with that mixture of ions, I could ask you to selectively precipitate one ion from the solution before the other. And then last but not least, I could ask you about the solubility of a particular solute as a function of the pH of the solution. A couple of these problems you have seen last year in our first year chemistry course, but some of them are going to be brand new to us this year. So we're going to kind of in the next couple of slides approach each of these different problems and give you some ideas about some commonalities between them that will allow you to solve them when you experience a new or different novel way of looking at a particular solubility question on the AP test. So let's move on to some examples here. All right, the first type of solubility problem we're going to approach here is the most straightforward type of problem you'll likely experience. That is a direct calculation of the solubility of a particular solute based upon the value of the equilibrium constant Ksp from its dissociation equation. So in this problem, example 1, I'm going to ask you to find the solubility specifically in units of grams per liter of the solute silver phosphate Ag3PO4, given a value of the equilibrium constant Ksp of 1.8 times 10 to the negative 18th for this particular solute. Now, as a starting point here, folks, a lot of these problems are going to have a similar approach, so I'd like you to do the same things every single time you face a solubility problem. The things I want you to accomplish each and every time are, number 1, I would like you to write for me a dissociation equation of the solute showing it breaking apart into its component ions. And then from that dissociation equation, I would like you to write a Ksp expression governing the equilibrium of the system. So let's go ahead here and take a look at our solute, which again is Ag3PO4. And recall again, as the dissociation occurs, those polar water molecules are going to exert those strong ion dipole attractions to the ions in solution, causing them to separate apart from one another into, in this case, 3 silver ions. Those are Ag1 positive. And then the polyatomic grouping of PO4 3 negative. So here is my dissociation equation, and again I'm going to write this as a reversible reaction, recognizing that the rate of dissociation is equal to the rate of ion recombination once this system establishes equilibrium. So I have my equation. The next thing I can do is, for an equilibrium system, write the K expression that governs that equilibrium. And again, as always, the K expression is defined as the ratio of concentration of the products over the reactants. So my K value here will be the concentration of the silver ion, which gets cubed, again recognizing that the dissociation produces 3 silver ions. And we're going to multiply that by the concentration of the phosphate ion in our solution. And again, recall, we do not have anything in the denominator here because on the left side of my equation, we had a solid phase species, which does not get counted in our calculation of the equilibrium constant. So I've got a Ksp expression now as well. And recognizing again that all of this is based around equilibrium chemistry, let's go ahead next and use that equation we just wrote to set up an ice table. Now, the ice table we set up here is going to be fairly simple because, again, on the left side of our equation, recall the only species present is that solid solute, so we can essentially just ignore the presence of that solute here as we look at the changes in concentrations of these ions in solution. Now, initially, both silver ions and phosphate ions should not be present in a pure water solution, and as such, I'm going to go ahead and include concentrations initially of 0 molar for each of those ions in our solution. At this point, now what I'm going to do is recognize that some amount of that solute is going to dissolve. So I'm going to go ahead and make the assumption here that some amount X moles per liter of the solute Ag3PO4 dissolves as the system establishes equilibrium. That value X that we are assuming dissolves into solution is an amount which we call the molar solubility of the solute. By definition, it is the number of moles per liter which are going to dissolve in our system. So if X moles per liter of the solute dissolve, because there's a 1 to 3 molar ratio there, I would expect to see the formation of 3x moles per liter of the silver ion and x moles per liter of the phosphate ion in solution. And again, because we started off at initial concentrations of 0, that means that the equilibrium concentrations of these ions would respectively be 3x molar for the silver ion and x molar for the phosphate ion in our solution. So we now have an ice table, and we can apply what we've learned previously to solve the ice table in this system. We're going to go ahead and take those equilibrium concentrations defined in terms of x and plug them into our KSP expression. This yields for me here then a value of KSP, which was again 1.8 times 10 to the negative 18th. That value would be equal to silver's concentration of 3x molar, which gets cubed, times the phosphate's concentration of x. And I can now simplify and solve here. I can cube everything inside my parentheses there, so be very careful to make sure you cube everything. 3 cubed is 27. X cubed times x would be x to the 4th power. So this expression simplifies down to 1.8 times 10 to the negative 18th is equal to 27x to the 4th. And recognize here, folks, that I don't have to find myself in a position here of making any assumptions because I can solve this directly in our system by simply dividing both sides of my equation by 27, canceling that out on the right side of my equation, and then taking the 4th root of both sides of the equation to solve for x. And as I do so, I get the value of the 4th root of 1.8 times 10 to the negative 18th divided by 27. Plugging that into my calculator, I get a value of 1.6 times 10 to the negative 5th molar. Now, having done the math, let's think about what we just found. Recall that in solving this ice table, we assumed that x moles per liter of that solute would dissolve, which means the x value we just found right there literally is the molar solubility of our dissolving solute. So I know now the molarity of silver phosphate, which will actually dissolve into solution. But in this particular problem, I was not asked for the solubility in molarity. I was asked for the solubility in units of grams per liter. So all that remains here is a real quick unit conversion to make my final calculation. I'm going to set up a quick monorail here. Monorail! And as I set up that monorail, I'm going to see here that I can write now the molar solubility as 1.6 times 10 to the negative 5th moles of silver phosphate per liter. So as the molarity is really a compound unit, I'm going to put the moles in the numerator and then liters in the denominator, recognizing that this really is moles per liter. That's my molarity here. And now a real quick conversion from moles into grams will allow me to find then the solubility in units of grams per liter. So I'm calculating here the molar mass of my silver phosphate, Ag3PO4. From my calculations, I get a molar mass of 418.58 grams per mole. So in my denominator of my monorail, I'm going to put per 1 mole of Ag3PO4. We have 418.58 grams of Ag3PO4. And notice now, as I cancel out my units, moles of silver phosphate cancels with moles of silver phosphate in the numerator and denominator, leaving me now with grams of silver phosphate per liter of solution dissolved. I can simply solve my monorail now, and I calculate here a value of 0.0067 grams of silver phosphate dissolved per liter of our solution. All right, so we've done the math. Now let's do the thinking to think if this is a logical answer. The KSP value of this equilibrium system, again, was 1.8 times 10 to the negative 18th. And recall that this very, very small KSP value implies that the system heavily favors the reactant side. And remember, from a solubility expression in a dissociation equation, on the reactant side is that dissolving solute. So long story short, what that really means is small KSP values means the system favor the reactants, which is where the undissolved solute lies. So a small KSP should really tell me then that this is a highly insoluble compound. And as such, you'll notice that only a very, very tiny amount, so that's almost about 7/1000ths of a gram, will dissolve per liter of this particular solute. That small solubility then correlates very well to what we understand here from our KSP. And again, this also tells me something important, which is even highly insoluble substances like silver phosphate, to a very small degree, do dissolve into solution. It's just that that equilibrium, again, lies heavily to the left side of our equation. All right, so we can now solve the most basic type of solubility problem. We can find a solubility from data about the KSP. Let's move on now to make a comparison of solubilities. All right, on our previous slide, having now looked at how to find the solubility from a given value of KSP, we came to the understanding that the value of the KSP really is a numerical reflection of how soluble the substance actually is. That is, in general, the larger of the value of KSP, the more heavily the system favors the product side, and therefore the more heavily disassociated it will be in solution. Now, that might lead us to believe that we could then make a comparison of KSP values to determine the relative solubilities of two different solutes. And as it turns out, in some cases, that is in fact true. So let's go ahead and take a look at this table that I've given you on the left side of our page right here, in which I've given you information about the relative KSP values of two different ionic compounds, which are number 1, lithium fluoride, and number 2, calcium carbonate. The KSP value of lithium fluoride is given as 3.8 times 10 to the negative third, whereas the KSP value of calcium carbonate here is listed as 2.8 times 10 to the negative ninth. Now, in making a comparison here using those KSP values, I see that the KSP value of lithium fluoride is orders of magnitude larger than the KSP value of calcium carbonate, implying therefore that lithium fluoride, upon its dissociation, more heavily favors the formation of those dissociated ions as products, and therefore is more likely to dissolve into solution than calcium carbonate. So comparing these two, I'm going to make the prediction here that lithium fluoride is significantly more soluble than calcium carbonate, given its much larger value of KSP. Now, that being said, have a look here now at the table over on the right-hand side, in which I give you two more species. These are calcium fluoride and calcium sulfite. The relative KSP values of calcium fluoride and calcium sulfite are 5.3 times 10 to the negative ninth for calcium fluoride and 6.8 times 10 to the negative eighth for calcium sulfite. So if I were to apply the same logic I just did on the previous example on the left-hand side over there, I would see that calcium sulfite has a larger KSP, which might initially make me think that in fact that is a more soluble substance. That being said, please be very, very careful when comparing two species, because as it turns out, in this case, we cannot directly compare their KSP values to determine their relative solubilities. And in order to understand why, let's take a look at finding their actual solubilities here using the approach we used on our previous example slide. So let's go ahead here, and we're going to go through and find the solubilities of these two different solutes. That is, first calcium fluoride and then calcium sulfite. Recall, for finding the solubility, the first thing I want to do is to write a dissociation equation. For calcium fluoride, as it dissolves, this would separate into the component ions, which are the calcium ion Ca2 positive and two fluoride ions F negative. And again, this is going to be dissolving in an equilibrium state. And from that, I can now go ahead and set up my ice table here, again ignoring the solute on the left side because this is solid phase, and giving initial concentrations of zeros for both of those ions in solution. Again, we're going to make the assumption that some amount, x moles per liter of the solute will dissolve, and for every x moles per liter of the solute that dissolve, we would form x moles per liter of calcium ions and 2x moles per liter of the fluoride ion according to the molar ratios from that dissociation equation, leaving me with equilibrium concentrations of x and 2x respectively for calcium ion and fluoride ion. Now I've written a dissociation equation instead of the ice table. Let's now write the KSP expression. The KSP is going to be equal to the concentration of calcium ion times the concentration of the fluoride ion squared. And according to the same pathway we showed you on the last slide, we'll now solve for the solubility x in this system by plugging in the value of KSP into our expression of 5.3 times 10 to the negative ninth. That would be equal to now our equilibrium concentration of calcium ion, which was x moles per liter, times the fluoride ion's concentration of 2x moles per liter, which gets squared. Now we're just going to simplify our math here. That gives me 5.3 times 10 to the negative ninth is equal to now 2 squared is 4, x squared times x gives me x cubed. I can now solve for my x value here by dividing both sides of my equation by 4 and taking the cube root of both sides, and that yields for me here a value of 0.0011 molar for my X value in this system. And recall, per our conversation, the X value in a solubility problem is always equal to the molar solubility of that dissolving solute. So 0.0011 moles per liter of my calcium fluoride will have dissolved into our solution. All right, so far so good. Looks just as we expected it to. Now let's do the exact same process, but now for the solute calcium sulfite. Again, writing my dissociation equation, I see calcium sulfite dissociates into calcium ions and sulfite ions. From that, I can set up my ice table again. My initial concentrations of both ions in solution will be zeros, but now my change in concentration will be different than in the previous example problem. Because the solute dissociates in a 1-to-1 molar ratio into the component ions, I would see then, respectively, a change in concentration of plus X moles per liter for both the calcium ion and for the sulfite ion, leaving me with equilibrium concentrations of X moles per liter for both ions. Now from here, I can again write the KSP expression. KSP would now be equal to the concentration of my calcium ion Ca2 positive times the concentration of my sulfite ion SO3 2 negative. And now plugging in my equilibrium concentrations into that KSP expression, I get now an expression which comes to the KSP of 6.8 times 10 to the negative 8th is now equal to X times X moles per liter, which again would be X squared. And then all I need to do here is to square root both sides of that equation, and that yields me an X value here of 2.6 times 10 to the negative 4th molar for my molar solubility of calcium sulfite. So let's now go ahead and make our comparison of those molar solubilities. You can see here now that the molar solubility of calcium fluoride, CaF2, is actually significantly greater than the molar solubility of calcium sulfite by almost an order of magnitude, even though the KSP value of calcium fluoride was smaller than the KSP value of calcium sulfite. And the reason why we see this apparent discrepancy is because the way we calculate KSP is different between these two species as a result of the fact that they dissociate to form different numbers of ions. And as you look at that, you then see that the KSP expression is not solved in the same way for both of these two equations. In one, the KSP was equal to 4x cubed, whereas in the other it was equal to x squared as we made that calculation. And because it's calculated in different ways, that implies, therefore, it's impossible for us to make a direct comparison of the relative KSP values of these two different species to determine their molar solubilities. You have to solve them using an ice table approach. Whereas on the left side of our page here, the species lithium fluoride and calcium carbonate, in that instance, we actually can directly compare their KSP values, because if you look at these, both of these two species here, lithium fluoride and calcium carbonate, follow the same pattern of dissociation. That is, both of them separate into a single cation and a single anion, implying, therefore, the KSP expression for both of these species would be calculated by simply finding the value of x squared. So again, as a kind of overall summary, if the species that you're comparing solubilities of dissociate to form the same number of ions in the same pattern, you can then directly compare their KSP values to determine which one will be more soluble. However, if the species dissociate to form different numbers of ions, in that instance, you'll need to use an ice table approach to compare the relative solubilities of these two species. All right, we are now through with the calculations of solubilities. Let's now kind of flip this on its head and do this backwards. We're going to go ahead and see if we could take a given solubility and use it to calculate a KSP value of a particular solute. All right, now having determined that we can calculate the solubility from a given value of KSP, let's do this backwards and see if we can calculate a KSP given information about the solubility of a particular solute. Now again, with all of these solubility problems, we always want to do the same initial steps for any given problem, which is to do all of those things we know how to do. We know how to write dissociation equations, we know how to set up ice tables, and we know how to write KSP expressions. So even though we're faced here with a new type of problem, we can still kind of fall back on all those things we already know how to do to give us an initial start to these problems. So let's go ahead and start by writing a dissociation equation for our solute, which in this case, in example 2, is bismuth iodide, BiI3. Upon dissociation, my BiI3 is going to separate apart into the component ions of Bi3 positive and 3 iodide ions I1 negative. So here's my dissociation equation. Let's now set up a ice table. Again, recognizing on the left side of the equation, I have my solid solute. I can ignore that. On the right side here, we'll have initial concentrations of both ions in an aqueous solution initially as 0. And as it dissolves, again, we're going to assume that some amount, x moles per liter of that solute will dissolve, yielding x moles per liter of bismuth ions and 3x moles per liter of the iodide ion. So again, I've got equilibrium concentrations of x and 3x respectively for bismuth ion and the iodide ion. There's my ice table. Let's now write a KSP expression. The KSP of this particular equation is going to give me the concentration of the bismuth ion, Bi3 positive, times the concentration of the iodide ion, I1 negative, which gets cubed from its coefficient in that equation. And as we've seen before, I can then plug in the equilibrium concentrations here into that KSP expression, which would be, again, x moles per liter for bismuth ion and 3x moles per liter for the iodide ion, again, which is getting cubed. And then simplifying that, that yields for me a value here of 3 cubed, which is 27, and x cubed times x is x to the 4th power. So I've got a KSP expression here, which is going to be defined by 27x to the 4th. Now recall, as per our previous conversation, in every solubility problem, the x value in these are going to be defined as the molar solubility of that dissolving solute. I was given information here not about the molar solubility, but instead about the solubility in units of grams per liter. So all I need to do now is to make another conversion now from grams per liter into moles per liter by setting up another quick monorail. And with this monorail here, I'm going to write it again as a compound unit. That is 7.78 times 10 to the negative 3rd grams of bismuth iodide per liter. So my grams go in the numerator, my liters goes in the denominator. And now I'm going to do a quick molar mass calculation for bismuth iodide. I find the molar mass of BiI3 to be 589.69 grams of BiI3 per mole of BiI3. And you'll see here again, units cancel out properly for me here. I see grams canceling with grams, leaving me now with units of moles per liter, or a molarity of that solute. And when I make my division here, I find a value of 1.32 times 10 to the negative 5th moles of bismuth iodide dissolved per liter of my solution. All right, so I now know the molar solubility, and remember, in these problems, the x value was defined as the number of moles of the solute that dissolved per liter. So the x value is my molar solubility, which means all I now need to do is plug that value of 1.32 times 10 to the negative 5th into the KSP expression for x. So again, KSP was 27x to the 4th. That now becomes 27 times that x value of 1.32 times 10 to the negative 5th, which gets raised to the 4th power. And we can go ahead and multiply out here. I now get a value of, it appears from my calculation, 8.18 times 10 to the negative 19th for the value of KSP in this problem. All right, stop again and think, does this answer make logical sense? I saw that a very, very small amount of bismuth iodide is dissolving per liter, and implying, therefore, this is a highly insoluble substance. Correspondingly, I find the value of the equilibrium constant KSP is a very small value of KSP, which again means this thing heavily favors the reactant side, implying, therefore, not a whole lot of that bismuth iodide is going to dissolve into solution as it establishes its equilibrium. Perfect. All right. So we can now go backwards here in the step. And again, the key idea is to remember that the x value in these problems is the molar solubility of the dissolving solute. All right, one more example here. Now example number 3. In this problem, we're going to give you a slightly different way of approaching this here. This time I'm going to tell you that we prepare a saturated solution of lead-2 bromide, that is plumbous bromide, by dissolving solid lead-2 bromide in water. And I find that when I dissolve that solute into water, the concentration of dissolved lead ions, Pb2 positive, is 2.14 times 10 to the negative second molar. And from this data, I want to calculate the value of KSP. Now, this is a little bit different approach because rather than giving you the solubility of the solute, instead I've given you a concentration of one of these ions in solution. But again, fall back on the things you already know how to do, and then we'll see a path forward. Let's start off again by writing our dissociation equation. That solute PbBr2 is going to dissociate into the lead 2 ion, Pb2 positive, and 2 bromide ions, Br1 negative. And with this dissociation equation, I can now set up an ice table. Again, ignoring the solute because it's solid phase. If I have initial concentrations of both ions in solution of 0, I would see a production of x moles per liter of the lead ion and 2x moles per liter of the bromide ion for every x moles per liter of the solute that dissolve. And that would leave me now with equilibrium concentrations again of x and 2x respectively for the lead 2 ion and the bromide ion. So I've got my ice table set up. I can now write my KSP expression. The KSP for this system is going to be the concentration of the lead 2 ion, Pb2 positive, times the concentration of that bromide ion, which gets squared, again, from the coefficient from the dissociation equation. Plugging in the equilibrium concentrations defined in terms of x into that expression yields here now a KSP value, which would be equal to x moles per liter for the lead ion times 2x moles per liter for the bromide ion, and that 2x is going to get squared. And then simplifying this down here, 2 squared is 4, x squared times x gives me x cubed. So my KSP expression here is going to give me 4x cubed. All right, so now let's think about what we know. I was given here a value of the equilibrium concentration of the lead ion, Pb2 positive. And looking back to my ice table, recognize that for every 1 lead ion that's produced in solution, one of those PbBr2 molecules must have dissociated into solution to produce that lead ion. That is, there's a 1-to-1 molar ratio between those two species, which implies, therefore, really here, the X value in this system, that is the molar solubility of this solute, is the same thing as the concentration of that lead ion in solution. So in this problem, I was literally given X in our problem here. And that makes my life very, very easy. Because at this point, I can now go ahead and just take that X value of 2.14 times 10 to the negative 2 and plug it into the value of my KSP expression, which again was 4x cubed. So 4 times the X value of 2.14 times 10 to the negative 2 cubed yields for me here a calculated KSP value of 3.92 times 10 to the negative 5th. Again, a relatively small KSP, implying a relatively insoluble solute. All right, so again, keep in mind that big key idea that in these problems, the molar solubility is the value of X in these problems. All right, we've seen a couple more examples here. Let's move on to some things which might look a little bit less familiar from last year. All right, in our next examples, we're going to take a look at how we can determine whether or not a precipitate will form upon mixing together two aqueous solutions. This should be a fairly familiar concept qualitatively from a lab which you completed last year, which was our ionic drops lab. And if you recall, in that lab, we mixed together a huge variety of different possible cations and anions to see which of those combinations would form precipitates in solution. And as we saw, several of those substances formed very, very insoluble precipitates. Several of them remained dissolved in the solution after mixing the two together. So the goal of this now is to quantitatively predict when a precipitate will actually form. And in order to do that, we're going to have to make use again of our dissociation equation and the KSP expressions. Recall, for the dissociation of an ionic solute, again, I've given you a generic formula here, which is CXAY, that will dissociate into the component cations and anions that would give me here X moles of C positive ion and Y moles of the A negative anion in solution. And from that, I could write a KSP expression, which would be the concentration of the cation, C positive, raised to the X power, times the concentration of the anion, A negative, raised to the Y power. Now, with that KSP expression, consider for a moment here a highly soluble solute like, say, table salt. if I mix together two ionic solutes that contain sodium ions and chloride ions, it's unlikely to see sodium chloride precipitate from solution because sodium chloride is a highly soluble substance. That being said, remember that even highly soluble substances have a point where they'll reach their saturation point in solution. That is, when the ions become high enough in concentration, the rate of ion recombination is going to equal the rate of dissociation of the solute, and you'd expect to see the formation of a precipitate. So really, the formation of a precipitate is quantitatively dependent upon the concentrations of the ions that we find in solution. Some highly soluble substances might in some cases form precipitates. Some highly insoluble substances, to a small degree, will dissociate, and therefore if they're low enough in concentration in solution, they might not even precipitate at all. So what we need to show here is how high the concentrations of these ions are in solution relative to how high they would be were the system completely saturated at its point of equilibrium. And this should at this point now start to sound a little familiar. We're comparing a current set of conditions versus an equilibrium set of conditions. This sounds like a fantastic opportunity for us to make a comparison of the value of the reaction quotient Q in comparison to the value of the equilibrium constant K. Now recall from our previous conversations around Q calculations, if the reaction quotient Q is greater than the value of the equilibrium constant KSP, that would imply a system which currently has too heavy a concentration of products, and therefore to establish equilibrium would need to shift to the left to remove product from the system. And remember, in these dissociation equations, the left side of our equation is where we find the solute that is dissolving. So if Q is larger than K, we would shift left, leading to the formation of that precipitate. Conversely, if we had a value of Q which was less than K, that would imply under the current conditions, the ions in solution would be lower in concentration than they would be were the system at equilibrium, which implies, therefore, our rate of ion recombination is going to be less than the rate at which those solute molecules would be dissociating. And as such, at that point, we would see the system shift to the right to establish equilibrium, which means we are going to have currently an unsaturated solution, and we will not see the formation of a precipitate in our system. So long story short, to solve these problems, we're going to first mix together two solutions. When those two solutions mix together, the total volume of the solution is going to go up, which implies the concentrations of all ions in solution will therefore go down. So we're first going to use the dilution equation to find the concentrations of the ions in solution upon mixing. And then once we have done so, we will then solve for the reaction quotient Q to determine the direction of shift as to whether or not a precipitate will likely form. Let's see an example of this on our next slide. All right, so we're going to take a look here at predicting whether or not a precipitate will form from a particular mixture of two solutions. The two solutions we're going to mix together in this example problem are number one, 100 milliliters of 0.0010 molar lead 2 nitrate. And number two, the second solution, is 200 milliliters of 0.0015 molar magnesium chloride. Now, before we go anywhere into the actual calculations here, let's just make some qualitative predictions about what we actually care about in our solution first. If I write a reaction between lead 2 nitrate and magnesium chloride, I would expect to see a double replacement reaction take place in which we would form the products, which would be lead 2 chloride, PbCl2, and magnesium nitrate, MgNO3 2. Now, from our discussion of qualitative solubility rules earlier in the year, recall we told you that one of the things the AP test requires you to just know is that all nitrate compounds tend to be highly soluble in solution, implying I do not expect to see the formation of magnesium nitrate as a possible precipitate in this system. Really, the thing that I'm kind of interested in here is the lead 2 chloride, the PbCl2, recognizing again that many lead compounds tend to be generally fairly insoluble. So I'm going to focus my attention here on the lead chloride as the possible precipitate from this system. And again, because this is a solubility problem, I'm going to start by doing all the things that I know how to do, which is to write a dissociation equation and a KSP expression. So to begin with, the lead 2 chloride, PbCl2, will dissociate into Pb2 positive ions and 2 Cl1 negative ions. And now, having written that dissociation equation, I can now write a KXP expression that governs this equilibrium. My KSP would be equal to the concentration of the lead-2 ion, Pb2 positive, times the concentration of the chloride ion, Cl negative, which gets squared. So I have a value of KSP. Now, at this point, I again wanted to make a comparison of the current state of the system versus the state of the system were it in equilibrium, recognizing again that the equilibrium point is the point of saturation of my solute. So this sounds very much like we need to make a calculation of the reaction quotient Q for this system, which will allow us to compare the current state of the concentration of the ions in solution to what those would be were they in equilibrium at their point of saturation. So with that plan in mind, as a starting position, consider that when we mix these two solutions together, the total volume of the solution is going to increase, and as such, when that total volume increases, the concentrations of all ions present in the solution will decrease according to our dilution equation. So as a starting point for this calculation, I want to determine both the concentration of the lead-2 ion in solution, as well as the concentration of the chloride ion, so that I can solve for my Q calculation. So let's go ahead and use our dilution equation to make those concentration calculations. Now, the initial concentration of the lead-2 ion from my solution was 0.0010 molar from that lead-2 nitrate. So I'll label that as my initial molarity M1. The initial volume of that solution was given to me in the problem as 100 milliliters. And upon mixing the solutions together, when I add the 200 milliliters of the magnesium chloride solution, the final volume will then be, assuming they are additive, a final volume of 300 milliliters. So I've got my M1, my V1, and my V2, and we'll now apply our dilution equation, M1V1 equals M2V2. A quick rearrangement there will solve for the final molarity M2 of our lead-2 ion, which would be M1V1 over V2. And plugging in my values given, we had 0.0010 molar lead ion at 100 milliliters for my V1, divided by the final volume of 300.0 milliliters. And when I solve here, I get a final molarity of the lead ion of 0.00033 molar. So I've got my concentration of lead-2 ion in solution. Let's now do the same thing for the chloride ion, but you have to be very, very careful here to watch out because there is a major point where people tend to miss this problem coming up. So again, having a look here at the concentration of the chloride ion, recognize that the source of the chloride ions in this solution is my magnesium chloride, MgCl2. And as we recognize that magnesium chloride upon dissociation in solution yields both a magnesium ion, Mg2 positive, and two chloride ions, Cl negative, if magnesium chloride is at 0.0015 molar, that would imply my chloride ion concentration must therefore be double that, as there's a 1 to 2 mole ratio between the magnesium chloride and the chloride ion upon its dissociation. So that implies the chloride ion concentration must therefore be 0.0030 molar in our solution initially. So that would be my M1 of 0.0030 molar for the chloride ion. The initial volume V1 is 200 milliliters, and the final volume V2, assuming again they're additive, is 300 milliliters. Again, calculating my final molarity M2, I get M1 V1 over V2, which would be 0.0030 molar times 200 milliliters divided by 300 milliliters, yielding for me a final molarity after dilution of 0.0020 molar chloride ion. So now that I've taken care of the dilution portion of my problem, I now know the concentrations of these ions under their current conditions. Let's now compare what those concentrations are to what they would be were they in equilibrium at their point of saturation with a Q calculation. Recall Q is the exact same expression as the expression for KSP. It just uses current concentrations rather than equilibrium concentrations. So given that KSP is equal to the concentration of that lead-2 ion times the concentration of chloride ion squared, I will now make a Q calculation with my current concentration of lead ion, again of 0.00033, times the concentration of chloride ion, which is calculated there, of 0.0020, and again that gets squared in our calculation. And upon calculation of my value of the reaction quotient Q, I find here a value of 1.3 times 10 to the negative 9. Now at this point, recognize that the entire point of calculating a value of the reaction quotient Q is to compare it to the equilibrium constant KEQ. So I see here my Q value of 1.3 times 10 to the negative 9 is significantly smaller than the given KSP value of lead 2 chloride of 1.6 times 10 to the negative 5th. So as my Q value is smaller than KSP, that implies a system which will shift to the right in order to establish equilibrium. And remember, the equation we're dealing with here again is the dissociation equation. A shift to a right in the dissociation equation implies a shift towards the dissociated ions, implying, therefore, this solution is not yet at its point of saturation, and therefore it is unlikely we would see a precipitate form within our solution. So long story short, as a summary, when dealing with a problem to determine whether or not a precipitate will form, you generally have 2 steps to go through. Number 1, step 1 is to determine the concentration of all ions in solution which may be involved in the formation of a precipitate, generally by using your dilution equation. And then once you have found those concentrations of those ions, make a comparison between the reaction quotient Q and the equilibrium constant KEQ to determine the direction of shift to establish equilibrium. If Q is less than K, we would shift towards the right, towards products, implying no formation of precipitate. In the opposite event, if the Q value is larger than K, that would imply that your current concentration of ions is greater than they would be were they in equilibrium in a saturated solution, and therefore to reach equilibrium, the system must shift to the left towards the position where that undissociated solid lies, therefore implying the likely formation of a precipitate. All right, another example down. Let's move on to another type of problem. All right, we find ourselves here with yet another type of solubility problem to deal with. This one's significantly different in approach from the ones we've seen thus far. But that being said, remember, there's always those things we always know how to do with solubility problems that we can kind of fall back on in order to think about a pathway forward when faced with a new type of problem. So to start with here, let's read through the problem. We have a solution which contains a mixture now of ions, that is a solution of 0.10 molar sodium sulfate and also 0.015 molar sodium carbonate, which are all mixed together. Now, to that solution which contains a mixture of different ions, we're now going to add very slowly the lead 2 ion to our solution. And the question is asking us here, which compound will precipitate first from the solution upon the addition of our lead? So we call this a selective precipitation of ions problem, and as it turns out, it's a very important problem in terms of understanding how industrial chemistry works, especially within the area of, say, mining, where you might end up with a mixture of a variety of different metal ions in solution, of which you want to separate the components of that mixture for further processing. So let's go ahead and take a look at an approach to this problem. And again, we have 2 possible precipitates which could form here. Those are, first, we might see the precipitation of lead 2 sulfate, whose KSP value is given there as 1.3 times 10 to the negative 8th. Or alternatively, we might initially see the precipitation of lead 2 carbonate, whose KSP value there is given as 1.5 times 10 to the negative 15th. Now, before you immediately go and choose the lead 2 carbonate, because it has a smaller value of KSP and therefore is less soluble, also notice that within our solution, the concentration of the carbonate ion is smaller than that of the concentration of the sulfate ion, which implies, therefore, it might need to have some further mathematical proof to justify our prediction as to which would precipitate first from that solution. So as the suggestion to you here, with any solubility problem, I always would like you to think about the precipitates which might form, and then for those precipitates to write dissociation equations. So let's go and do that first. Beginning with the lead 2 sulfate. That lead 2 sulfate upon dissociation, were it to precipitate, would form the lead 2 ion Pb2 positive and the sulfate ion SO4 2 negative. Now conversely, if we were looking at the lead carbonate precipitate, that one is governed by the equilibrium from its dissociation equation. Lead 2 carbonate upon dissociation would form the lead 2 ion Pb2 positive and the carbonate ion CO3 2 negative. So we have dissociation equations for each of the possible precipitates that they're forming. Let's also now write a KSP expression that would govern each of those equilibria. For the lead 2 sulfate, our KSP would be equal to the concentration of the lead 2 ion, Pb2 positive, times the concentration of the sulfate ion, SO4 2 negative. And alternatively, looking at the lead 2 carbonate, the KSP value would be the concentration of the lead 2 ion, Pb2 positive, times the concentration of the carbonate ion, CO3 2 negative. Now, at this point, before we start getting into messes like solving ice tables, let's recognize that I already know a large amount of information about these systems were precipitates to actually form, because recall, a precipitate forms when the solution is itself saturated, which implies at the point when the Q value is equal to the value of KSP. Now, I happen to currently know the concentration of the sulfate ion already in my solution, and I also happen to know the KSP value of the lead-2 sulfate, which would be equivalent to the Q value were the solution saturated. So really, I know everything out of that KSP expression for our dissociation, with the exception of what must the lead-2 ion concentration be in that solution to cause precipitation to occur and saturate that solution. So really what I could do here is simply rearrange the KSP expression and solve for the required concentration of lead to be present in a saturated solution. So let's go ahead and do that. The concentration of lead-2 ion would be equal to the value of the KSP divided by that concentration of sulfate ion SO42 negative. And let's now calculate that concentration by plugging in the respective KSP and concentrations given to me from the problem. Our KSP was 1.3 times 10 to the negative eighth, and the concentration of sulfate ion in our solution was given to me as 0.10 molar, recognizing again that sodium sulfate dissociates in a 1-to-1 molar ratio into sulfate ions. So therefore, I can calculate my concentration of lead required to form that precipitation, and I find here a value of 1.3 times 10 to the negative 7th molar lead-2 ion would be present in a saturated solution of lead-2 sulfate, were the concentration of sulfate ion again 0.10 molar. All right, now let's go through the exact same approach, but now with the carbonate compound. Solving again for the concentration of lead-2 ion required to precipitate the carbonate ion out of the KSP expression. Doing a quick division there gives me the concentration of lead-2 is equal to the KSP divided by the concentration of the carbonate ion, CO3 2 negative. And again, plugging in the given KSP value of 1.5 times 10 to the negative 15th, and dividing that by my concentration of carbonate ion, which is 0.015, I find now a required concentration of lead-2 ion of 1.0 times 10 to the negative 13th molar, necessary to saturate a solution of lead-2 carbonate and therefore cause precipitation. And now I have enough information to determine which of these compounds will precipitate first. Remember from the description of our problem, we assume here that we are starting off with essentially no lead present in our solution and then very slowly adding that lead-2 ion to the solution, implying the concentration of lead is gradually going to be going up. And therefore, whichever of these lead concentrations is the lowest would be the one which is therefore going to be reached first in the solution and therefore cause the first precipitation to occur. So because the required concentration of lead-2 ion is smaller to precipitate lead carbonate than the required concentration to precipitate lead sulfate, I'm going to make the prediction here that the lead-2 carbonate will be the first compound to precipitate from our solution. All right, so with another solubility problem taken care of, we can now move on and have a look at how the pH of a solution will affect the solubility of a dissolving solute. All right, for the next couple of slides, we're going to be looking at how solubility of a particular solute might be affected by other things present in the solution. And in particular, we want to have a look at how the pH of a solution might affect the solubility of our solute. So to begin with, let's examine a salt that we might expect is going to be highly pH dependent. That would be a hydroxide salt. If we have a look here at magnesium hydroxide, upon dissociation, the solute magnesium hydroxide would dissociate into magnesium ions, Mg2 positive, and 2 hydroxide ions, OH negative. And if we recognize that pH is a function of the concentration of hydrogen and hydroxide ions in the solution, it should seem logical then that this particular solute would be very pH dependent in its solubility based upon our understanding of the common ion effect. So consider if we had a strongly basic solution. A basic solution would mean we have increased the concentration of hydroxide ions in that solution, which would therefore increase the rate at which magnesium ions bump into those hydroxide ions within solution. That should have the net effect of shifting this equilibrium to the left towards the undissociated solute, implying magnesium hydroxide is probably significantly less soluble and less likely to dissociate into solution if the pH of our solution is very, very high. Now conversely, in a strongly acidic solution, there's an abundance of hydrogen ions present. And as we're familiar, hydrogen ions are likely to combine together with hydroxide ions in solution to form water. And as such, the addition of hydrogen ions into solution, if the pH were very, very low, would have the net effect of consuming hydroxide ions, decreasing the rate at which magnesium ions bump into those hydroxide ions within solution. This would in turn decrease the rate of our reverse reaction, and therefore we would expect to see an equilibrium system shift to the right towards the dissociated ions in solution, implying magnesium hydroxide would likely become much more soluble and likely to dissolve into solution if the pH were very low in an acidic solution. So we see here that hydroxide salts clearly are going to be dependent upon the pH for their solubilities. Now, another salt that might be a little bit less straightforward to understand here is going to be maybe a carbonate salt, or another salt that contains an anion that effectively can act as a base. So have a look here at calcium carbonate, CaCO3. Calcium carbonate, upon dissociation, separates apart into calcium ions, Ca2 positive, and the carbonate ion, CO3 2 negative. Now, we are interested here in the carbonate ion because the carbonate ion is the conjugate base of carbonic acid. And as such, because carbonic acid is itself a weak acid, that implies the carbonate ion is a relatively strong conjugate base. So consider now the effect of adding an acid into the solution and thereby lowering the pH of our solution. Upon the addition of the acid, the H positive ions from that acid would be expected to combine together with the carbonate ion, CO3 2 negative, forming the bicarbonate ion HCO3 1 negative. And the net effect of this is we would expect to see the concentration of carbonate ions in our solution decrease, again causing a decrease in the rate of our reverse reaction in our dissociation equation, and therefore an equilibrium shift to the right. Now that implies that calcium carbonate would therefore be more likely to dissolve into solution were the solution strongly acidic. And as it turns out, this actually has some real-world applications in a couple of different interesting places. First of all, have a look here at the picture over on the right side of your screen. This is a picture of Carlsbad Cavern, a cavern which is entirely formed by limestone deposits forming those gigantic stalactites and stalagmites. Now, to understand this phenomenon, consider rainwater that percolates through the ground, and as it does so, it picks up carbon dioxide. That carbon dioxide will then combine together with the water to form carbonic acid, H2CO3, essentially acidifying the rainwater. That acidified rainwater then leaks down into the cavern, and as such dissolves the calcium carbonate, and that calcium carbonate, again, we saw, was more soluble in acidic solutions. But then when that rainwater is then exposed to the larger atmospheric air, it has a tendency to then let go of the carbon dioxide which it had previously absorbed, in turn decreasing the solubility of the calcium carbonate, where it then reprecipitates out of solution to form those gigantic pillars. So limestone caverns like Carlsbad are one fantastic application of this concept. Another place where you might have seen it is in fact in cleaning solutions present in your house. You may have noticed some whitish deposits forming around the outside of your faucets, especially if you have what we call very, very hard water, which contains large amounts of dissolved calcium and magnesium ions. Those deposits are generally made up of things like calcium carbonate and magnesium carbonate. So if you want to clean those up efficiently rather than scrubbing away for hours and hours and hours, a very effective tool would be to simply use a weak acid like, say, vinegar, otherwise known as acetic acid. The addition of the weak acid vinegar has the net effect of decreasing the concentration of carbonate ions in solution as those carbonate ions pick up the acidic protons. And as such, we would again see an equilibrium shift to the right for the dissociation equation of the calcium carbonate, meaning that becomes more soluble in solution overall. So lots of places where we see this applied in the world around us. Let's now apply this idea to a quick example problem. One of the things the AP test is likely to ask you about is to identify which particular solutes might have some change in their solubility depending upon the pH of a solution. So let's look at two potential solutes here and determine which of these will be more soluble in an acidic solution. Starting off with that first solute, which is silver chloride. Now, if I write the dissociation for silver chloride, that solute would separate apart into the silver ion, Ag positive, and the chloride ion, Cl negative. And upon the acidification of a solution, I would in turn increase the concentration of hydrogen ions in solution, and the hydrogen ion of the species present could potentially react to the chloride ion. If it did so, however, the product it would form would be HCl. Now we know that hydrochloric acid HCl is a very, very strong acid, implying therefore that chloride ion is an incredibly poor base. So the reaction we've just written right here is a very unlikely reaction to occur, and therefore we're not likely to meaningfully change the concentration of chloride ions in solution by acidifying the solution overall. So I would expect silver chloride to be essentially independent in its solubility of the pH of the solution. Now conversely, if we have a look at the other possible solute here, which is silver phosphate, upon dissolving silver phosphate in solution, it separates into the silver ion, Ag positive, of which we would find 3, and then the phosphate ion, PO4 3 negative. Now, whereas the chloride ion was the conjugate base of hydrochloric acid, a strong acid, the phosphate ion is the conjugate base of phosphoric acid, and phosphoric acid is itself a weak acid, implying therefore the phosphate ion is a relatively strong base in solution. Now, recognizing that that phosphate ion is a pretty fantastic base, that implies therefore that it's likely to pick up hydrogen ions in solution were the solution to be acidified. So in an acidic solution, that phosphate ion would likely therefore pick up hydrogen ions, forming a number of different products, but among them hydrogen phosphate or dihydrogen phosphate. And as such, the addition of hydrogen ions would have the net effect of decreasing the phosphate ion's concentration, and thereby, in our dissociation equation, we would see a decrease in the rate of ion recombination, and therefore a less likely formation of that precipitate silver phosphate. So logically speaking, I would expect silver phosphate to therefore increase in solubility within an acidic solution. Now let's take a look at this same idea from a quantitative perspective on our next slide. All right, on this slide here, we're going to take a look at a quantitative approach to determining the pH effect on solubility of a dissolving solute. And in particular, we're going to be looking here at calculating the molar solubility of ferric hydroxide, that is FeOH3, in a variety of different solutions. Those are a pure water solution, a solution where the pH is 11, and a solution where the pH is 5. So let's go ahead here and start by doing the things we know how to do in order to determine the molar solubility of a dissolving solute. That is, let's write a dissociation equation and set up a ice table and a KSP expression. So my ferric hydroxide, FeOH3, upon dissociation will yield ferric ions, Fe3 positive, and 3 hydroxide ions, OH negative. And from this, I'm going to go ahead and set up an ice table here. So we've got I, C, and E for my initial concentrations, my change, and my equilibrium concentrations of these species. And recognize again, because the ferric hydroxide is a solid phase solute here, I'm going to ignore it as part of my ice table and focus on those concentrations of ions. Now, initially in my pure water solution, the initial concentration of ferric ions should be 0. And under most circumstances, we have assumed previously that the initial concentration of an ion like the hydroxide ion should be pretty close to 0 as well. However, recognize here that this hydroxide ion really truly isn't exactly at 0 concentration in the initial pure water solution, but instead would be at a concentration of 1.0 times 10 to the negative 7th molar from the autoionization of water. Now, in most cases, that's safely ignored. However, when we have a very, very pH-sensitive solute, which we're trying to dissolve here, those little hydroxide changes in concentration might have a major impact on the overall solubility of our dissolving solute. So I'm going to include it here as an initial value in my ice table. Assuming again that X moles per liter of the ferric hydroxide dissociate upon dissolving, I would therefore see the formation of X moles per liter of ferric ion and 3X moles per liter of the hydroxide ion from my mole ratios from that dissociation, leaving me with equilibrium concentrations of X and 1.0 times 10 to the negative 7th plus 3X moles per liter for the ferric ion and the hydroxide ion, respectively. Now, from this position, let's now go ahead and write a KSP expression for our equation. The equilibrium which governs the dissociation here would be defined by the concentration of the ferric ion, Fe3 positive, times the concentration of that hydroxide ion, which is going to get cubed. And we can now go ahead and plug in our given values into this expression. Our KSP of 4.0 times 10 to the negative 38th would now be equal to the equilibrium concentration of the ferric ion, which was X from my ice table, times the concentration of that hydroxide ion, which was 1.0 times 10 to the negative 7th, plus 3X quantity cubed. Now at this point, recognize that this is a good opportunity for us to simplify our calculation by making an assumption. I'm going to go ahead here and assume that the quantity 3x is very, very small in comparison to the initial molarity of hydroxide ion in that solution, which is 1.0 times 10 to the negative 7th. Now this might seem like a tricky assumption to make because again, that initial concentration of hydroxide ions is not very high, but remember, this is a very, very highly insoluble solute, implying therefore not very much is going to dissolve and therefore my x value is probably going to be pretty small based upon the tiny value of that KSP. So if I make that assumption, my equation simplifies down to the KSP of 4.0 times 10 to the negative 38th is now equal to x times 1.0 times 10 to the negative 7th plus a tiny number which is essentially close to 0 here, so we'll get rid of the 3x, and then that quantity all again gets cubed. And solving from here, I can simply divide by the 1.0 times 10 to the negative 7th cubed, yielding for me here an x value of 4.0 times 10 to the negative 17th molar. A tiny, tiny, tiny x value, which again correlates to that very, 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 very small KSP, which we saw for our solute. Now again, I did make an assumption here, so let's prove it to show that it is in fact a valid assumption by taking my 3x value and dividing it by the thing I assumed it was small in comparison to. So 3 times that x value of 4.0 times 10 to the negative 17th, divided by 1.0 times 10 to the negative 7th, and then multiplying this by a factor of 100 to express this as a percentage, yields for me here a percent error introduced of 1.2 times 10 to the negative 7th percent, which seems well within our 5% rule there. We have no problems making this assumption. So remembering that from these equations, the x value always describes the molar solubility of the dissolving solute, I can therefore say we would see 4.0 times 10 to the negative 17th moles per liter of ferric hydroxide would be expected to dissolve in a pure water solution. Let's see how now this is going to change if we change the solution to a basic solution where the pH is 11. Now, everything we did in terms of setting up our ice table is going to be exactly the same in this situation, so I'm just going to go ahead and copy this and bring it down here. But recognize that I now have a different concentration of hydroxide ions in the initial solution due to our new pH. At a pH of 11, the pOH of the solution would be 14 minus that value for a pOH of 3, implying a concentration of hydroxide ions in this solution of 1.0 times 10 to the negative 3rd molar. So I'm going to include now this value as my initial concentration of hydroxide ions in our ice table. The same changes in concentration would be expected of plus x and plus 3x respectively, and therefore my equilibrium concentrations are now x and 1.0 times 10 to the negative 3rd plus 3x. So we'll do the same thing we did before. Inputting those values into my KSP expression now yields the KSP value of 4.0 times 10 to the negative 38th, which is equal to x times 1.0 times 10 to the negative 3rd plus 3x quantity cubed. And again, we'll make the same assumption we made before, that 3x is very small compared to that initial molarity of 1.0 times 10 to the negative 3rd. And that simplifies my expression down then to 4.0 times 10 to the negative 38th is equal to x times 1.0 times 10 to the negative 3rd quantity cubed. Now, solving for here, I find an x value of 4.0 times 10 to the negative 29th. Now, if you thought this was insoluble before, this is now just absurdly insoluble in this solution when the pH is 11, which should make logical sense based upon our understanding of essentially the common ion effect. If we see an increase in hydroxide concentration, that should increase the rate of the ion recombination in our solution, and therefore push our dissociations equilibrium to the left, implying this solute becomes even less soluble in a basic solution. Now again, I could check that assumption one more time here. This is clearly going to be well within our 5% rule here, so I'll just move on after having that assumption checked to the final step, which was, how is this now going to look in a solution where the pH is 5? Same idea, same dissociation. So again, I'm only going to change the initial concentration of hydroxide ions. So in my solution, a pH of 5 implies a pOH of 9, and therefore a hydroxide concentration of 1.0 times 10 to the negative 9th. So if I plug that now into my ice table, I see here an initial concentration of 1.0 times 10 to the negative 9th molar OH negative. And we'll just adjust here accordingly. The equilibrium concentration as well now becomes 1.0 times 10 to the negative 9th plus 3x molar. Same process as we saw in the previous two calculations. Now we will solve my KSP expression for x. So I have 4.0 times 10 to the negative 38th is equal to my x value times 1.0 times 10 to the negative 9th plus 3x quantity cubed. And yet again, making the assumption that 3x is very small now compared to that 1.0 times 10 to the negative 9th molar, simplifies my expression down to 4.0 times 10 to the negative 38th is equal to x times 1.0 times 10 to the negative 9th quantity cubed. And from this, I can now solve again for x, which yields here a value of 4.0 times 10 to the negative 11th molar for my molar solubility of our ferric hydroxide. Now that still seems like a very small solubility, but recognize compared to the molar solubility in the pure water, this is now literally 1,000,000 times more soluble than it had been in the pure water solution. So even a small change in pH from neutral at 7 down to 5 makes this solute 1,000,000 times more soluble. Imagine how much more soluble it would be if we used this now in a solution where the pH was maybe 1 or 2, and you can clearly see now how quantitatively there is a meaningful change in the solubility of this solute depending upon the pH of our solution. So we've now seen quantitatively a proof that our understanding of the common ion effect truly seems to be functional here in terms of determining the relative solubility and pH dependence of that solubility of a solute in solution. We got one more slide to go and then we will move on. All right, for a final application of equilibrium principles to solubility systems, let's have a look at the common ion effect as it applies to a solubility of a dissolving solute in a solution. So I'm going to ask you here to find for me the molar solubility of lead-2 iodide, that is PbI2, both in a pure water solution and in a solution of 0.010 molar potassium iodide, Ki. Given the KSP for this solute PbI2 is 1.4 times 10 to the negative 8th. Now we already know how to solve for the solubility of a solute in a pure water solution by writing a dissociation equation and solving an ice table. So let's go ahead and do that first. My solute PbI2 will dissociate into the lead-2 ion, Pb2 positive, and 2 iodide ions, I negative. And from here, I'm going to set up my ice table here, again, ignoring the lead-2 iodide as a solid phase species. And then on the right side here, my initial concentrations of both the lead-2 ion and the iodide ion will be values of 0 molar in a pure water solution. As some of that solute dissolves, for every x moles per liter of the solute that dissolve, we would produce x moles per liter of the lead-2 ion and 2x moles per liter of the iodide ion from that molar ratio of our dissociation equation, yielding equilibrium concentrations of x for the lead-2 ion and 2x molar for the iodide ion. So we've got an ice table, and now let's go ahead and set up our KSP expression. The KSP would be equal to the concentration of the lead-2 ion times the concentration of that iodide ion, which gets squared. And from here, we will insert our equilibrium concentrations defined in terms of x into that KSP expression. My KSP again was 1.4 times 10 to the negative 8th. That is now equal to the lead-2 ion's concentration of x times iodide's concentration of 2x, which again gets squared as a quantity. Simplifying this down yields 1.4 times 10 to the negative 8th is equal to now 4x cubed, and solving for x with my calculator gets me a value here of 0.0024 molar for that x value. Now recall again, the x value in any solubility problem is the molar solubility of that dissolving solute, and that means here that 0.0024 moles per liter of our lead-2 iodide would be expected to dissolve in a pure water solution when that establishes equilibrium. All right, so far so good, easy peasy. Now let's take a look at how the process will occur if instead of dissolving this in pure water, we try to dissolve the solute in a 0.010 molar solution of potassium iodide. My dissociation equation is the same, so we'll just go ahead and copy that and bring it on down, and we'll set up a new ice table. We still have an initial concentration of lead ion of 0 molar, but now my iodide concentration in this Ki solution would initially be 0.010 molar. And now we can, again, define the changes in concentration. It would be a plus X moles per liter for the lead-2 ion and plus 2X moles per liter for the iodide ion, yielding equilibrium concentrations of X and 0.010 plus 2X molar for the lead ion and the iodide ion, respectively. And from here, just as we did before, let's plug in those equilibrium concentrations into our KSP expression. The KSP value of 1.4 times 10 to the negative 8th is now equal to my X value times 0.010 plus 2X quantity squared. And again, this is a great place for a simplification by making an assumption. I'm going to assume here that 2X is very small compared to that initial molarity of 0.010 molar, which will simplify my expression now down to 1.4 times 10 to the negative 8th is equal to X times 0.010, which gets now squared. And solving for X here, I find an X value of 1.4 times 10 to the negative 4 molar. Now again, I did make an assumption to solve this here, so let's check that assumption by taking my thing I assumed, which was small, which was the 2X value, so 2 times 1.4 times 10 to the negative 4th, and dividing that by the initial concentration I assumed it was small in comparison to, of 0.010 molar, and then multiplying this by 100 to express this as a percentage. I find here that my assumption introduced approximately 2.8% error into my calculation, which again fits within our 5% rule, so we're going to go ahead and accept that assumption. All right, so now we've done the math, we now know that the molar solubility of our lead-2 iodide is now 1.4 times 10 to the negative 4th molar in the lead iodide solution. Now that is compared to the solubility in our pure water solution of 0.0024 molar. And you'll notice that my solute has become significantly less soluble in the potassium iodide solution than it was in the pure water solution. And this justifies really for me here what I already qualitatively understood from the common ion effect. That is, the presence of those iodide ions will have the net effect of increasing the rate of ion recombination in the dissociation equation, and thereby increasing that rate of the reverse reaction. This should be expected to then push that equilibrium to the left towards the undissociated solute, implying that we should see the formation of more precipitate, that is to say, it is less soluble in a solution which contains the dissolved common ion, the iodide ion. All right, so we now have quantitative proof that backs up our understanding of a qualitative concept we've seen earlier. As a hint to you as you approach these solubility problems, there is a huge different variety of the types of problems you're expected to be able to solve in the AP Chemistry test. So if you find yourself in a position where one of these things looks a little bit less familiar, always just fall back on those things you know how to do, which is to, again, write dissociation equations, write KSP expressions, and set up ice tables. And sometimes just going through those steps will jog your memory and help to point you in a direction of how to solve the problem, even if the path to the solution does not immediately jump out at you when you first look at the problem. So that's it for solubility chemistry here. Thanks for listening. We'll see you at the next lecture.